All right. Thanks for coming. In 2008, I saw a dance movie called Body Traces by choreographer Lisa Pata and artist Sophie Kahn. It's an exploration of the figure as captured by a stop-motion 3D scanner rendered with this ethereal lighting. I was working on my MFA, and they did a residency at my university in upstate New York. They gave this talk describing their process, and I was completely enamored by their dedication. Lisa would have to hold a pose for at least a minute to capture a single frame for the movie while this makeshift Lego contraption moved a laser line across her body. And the movie must have been hundreds of frames long, so you can imagine how this took a while. Knowing that it was possible to construct a 3D scan with only a laser line and a camera, I started to wonder what else was possible. I felt like it was making me reconsider what I could do with a camera or with light. So I read up on the technique and found out a laser line is just a laser pointer that has a special lens to project a line. And when you look at that projected line slightly off axis from the laser, then it looks kind of curved if it's hitting a curved surface. And that curve's a description of the shape of the surface. So a laser scanner just collects a bunch of these curves. And while I was thinking about this, I wasn't necessarily like trying to solve a problem, like making a faster 3D scanner or capturing in color in addition to shapes. For me, there was just something inherently beautiful about this relationship between this line of light and the surface of a scene or an object or a person. It felt like this kind of dialogue between the immaterial and the material world, and that empty space in between the light and the surface had this kind of openness where I could construct these imagined geometries of their relationship. And I remember it was a really cold winter in upstate New York, and as I was thinking about these in-between spaces, I had this like renewed admiration for the steam coming off of tea or some snowstorms where you could kind of look through them and see hints of these invisible volumetric wind patterns. The year before, I saw this music video for Radiohead for their song House of Cards, which was one of the first music videos to experiment with 3D scanning. And the press release for that video said, no cameras were used to make this video, no cameras or lights. So I thought, oh man, whatever tech they're using, it must be way too complicated to build and way too expensive to buy. So I'll never get to do anything like this, and I just kind of put it in the back of my head. But the deeper I got into these ideas with like the laser line scanner and reading about Sophie and Lisa's work, the more I wondered how exactly did they make this video? What was the tech behind it? So I started to look up the folks who did the research, and I discovered the dirty secret, which is that the press release was a lie. The 3D scanner was actually just a camera or a couple cameras and a projector. That was it. I mean, it looks really complicated because it like doesn't have a case, but it's just some electronics kind of soldered together, plugged into a computer. Instead of looking at the distortions of a single laser line, it's like they're projecting a bunch of lines at the same time. And they use a technique called three-phase scanning where they shift these kind of blurry lines across the face, and they compare the brightness at each pixel over a few frames to determine the shape of that figure, to figure out the shape. This general idea of using like projectors and cameras to scan things is called structured light. So I implemented this technique after talking to some much smarter professors at my school, and immediately realized there were some practical issues they didn't talk about in their paper. For example, like getting blasted with this stroboscopic projection from just a few feet away makes you want to close your eyes. So a lot of the first portraits I took had this kind of death mask quality to them. And it sort of reveals the structure of the scanning system in the subject's response to it. Once the stills worked, I tried to extend this to video, and it failed completely. So this is supposed to be a video of me kind of panning around the room to find my friend who was hanging out and helping me glue things together. But instead, it just kind of looks like some reject scene from Interstellar. And this might have been related to the fact that my 3D scanner was literally built from a shoebox and duct tape, barely holding the camera to the projector. But eventually I did get it working better. I got back in touch with Lisa Para to work on a new dance performance that incorporated this kind of scanner I was working on. And this is kind of what the scanning process looks like. And these were some of the first results we got. We really enjoyed this kind of glitchy quality that came out of it. It turns out in the Radiohead video, the reason their scans look glitchy is because they were purposely modifying the projection. They were putting like sheets of glass with rain in front of Tom York's face, and their scanner was like perfect. It didn't have the glitches that we had, so we had real glitches. This is a kind of behind the scenes video of what the scanner was doing. So one interesting thing to watch for is that whenever two parts of the subject get split up by a shadow or an occlusion, they can become completely unfixed from each other in depth. That's because this kind of three-phase scanner, it only understands relative depth, like how far one part of a thing is from the camera relative to another part of a thing. Not absolute distance. It doesn't know I'm 10 feet away or 12 feet away. So it gives you these really funny glitches where entire parts of a body or an object or a scene will kind of jump forward and backward. Like in this workshop, whenever she would move her hand away from her face, her entire head would kind of sink back into infinity. So the code couldn't really trace the relative depth across the black straps of her dress. They acted like this void that could not be sensed. These studies turned into an installation called the Janus Machine with a few friends, Zach Lieberman, Theo Watson, Daito Manabe. And it captures these brief 3D portraits from visitors. This might be one of the first times we managed to use like a 3D scanner like this in a way that kind of general public could interact with it. So there were a lot of kind of basic technical challenges to getting this working, but we were more importantly trying to create this poetic experience of seeing yourself kind of reflected in this point cloud that could assemble into any face, and trying to maybe understand what it means to have this relationship to other people that's being represented by the computer. Right after this piece opened, a really cheap 3D scanner was released to the market called the Xbox Kinect, which was a video game controller, which was in fact a 3D scanner. And a lot of the technical work I'd done on real-time 3D scanning up to this point was kind of made obsolete overnight. But I wanted to get back to that feeling of like imagined geometries or hinting at some kind of invisible complexity. I found this kind of really important missing ingredient during a residency in this VR space in Manchester at University of Salford. We played with some kind of complicated techniques like head tracking and 3D shutter glasses. And I learned something really important, which was that the most significant trick for creating an immersive space is to basically fill the space, which is to use your peripheral vision. More important than the head tracking, more important than the 3D glasses. As long as I felt like I was surrounded by something and that was moving or kind of setting up some kind of horizon line for me, I felt like I was in the middle of the space. So I guess I was trying to connect here, like how do I create these kind of imagined geometries, these imagined sculptures in a way that feels really immersive. And I wanted to try and connect these. So I thought, how do I fill a space with light? What's the quickest way to like get that kind of light? Like I don't have, $1 million to build my own VR space, and I'm not even sure that's like interesting to me. It's too kind of prescribed. So it turns out there's a really popular optical instrument that accomplishes this, which is the disco ball. It's a kind of optical splitter. So if you take a single bright light and you point it at your disco ball, it splits it into hundreds of beams, right? And if the disco ball moves a little bit, all of these beams move a lot. So it's a really interesting optical device, and it has a lot of cultural history, or some might say baggage, behind it. But I thought it was this kind of beautiful tool that accomplished this really functional thing that I was trying to do. So when the next festival asked me to propose new work, this was 2012, I said, can you get me 3 projectors and 50 disco balls? And I'll never forget the moment I stepped off this like 9-hour red-eye flight into this post-industrial warehouse space where the producer opened up this deep treasure chest and said, "You're lucky. a club went out of business recently. And I thought to myself, that's funny, you know, maybe the reason they went out of business is because they were buying too many disco balls. So the theme of that festival was collaboration. And they paired me up, this festival is called Click, it's north of Copenhagen. They paired me up with a creative coder named Jonas Yongyan to develop the piece. And so we worked together based on the 3D scanning research I'd done before to create this piece called Light Leaks, which we've been installing since then. And recently we had it at the Row in downtown LA. It took us a few days kind of figuring out how to calibrate everything. And eventually we were able to use a different kind of structured light technique, not the same as three-phase scanning, to calibrate all of these reflections in the space and recover 3D positions for all of them so that we could kind of render movement in a way that completely surrounds you. With all the lights turned off and these kind of huge abstract patterns spinning around, the room starts to dissolve and you sort of melt into this infinite space that doesn't really have clear boundaries or borders anymore. So for the impatient, if you watch the video of Light Leaks online, these first 10 seconds actually explain how it's made. But maybe that's too fast, so let's step through. And this is where this might get a little mind-bending. So good luck. I guess I'm not sure if I'm saying that to you or to me, but here we go. The first step in this whole process is to project a bunch of patterns that help us understand where the reflections are coming from. So one possibility would be to turn on each pixel one at a time, right? We've got one projector, it's pointing out the disco balls. We try the pixel in the middle. We kind of look around the room. So, oh, there it is. All right, you make a little note. Is that 3 meters? That 2 meters off there. All right, next pixel. Let's do it. Here we go. Oh, there it is. You know, and you could keep doing this, but there's about 33 million pixels. So even if you could do this with a camera, right, at 30 frames per second, it still takes 12 days to do that. It's not really an option. So instead, we take a kind of like divide and conquer approach. So first, we project black on the left and white on the right. And then we do the opposite, white on the left and black on the right. And now we get two pictures, right? If we compare these to each other, there's something really neat that happens, which is that whichever pixel in the camera image is brighter on the first photo and darker on the second one, that means it came from the left side of the left side of the projector, right? And if it's the other way around, if it's darker in this one and brighter in that one, it came from the right side of the projector. So that doesn't tell us much, right? All we know is whether it was the left or the right side. If we repeat this process, we can subdivide by 2. So now we do black, white, and then another one, white, black, black. So now we've got 4 frames to our camera, right? And we know now if it was brighter in the first pair and brighter in the second pair, well, it was on the far right. And if it was darker in the first pair and darker in the second pair, it was on the far left. And we can actually just keep doing this and repeating this process until we get like maybe 10 pairs of photos. And then we know exactly for every pixel in the camera image what the position on the x-axis of the projector, what the column was. All right, you still with me? I see some heads nodding. This is great. Then we repeat this process for the rows. So we divide top half as black, bottom half as white, right? Vice versa. So we've taken about 20 pairs of photos, around 40 photos, and now we know, once we look at those 40 photos, where every pixel in the camera space came from. So we've got some code to do this. We don't do it by hand. That code gives us these kind of encoded images, which I'm going to describe kind of what those look like and show you some examples. So this is an example when we did it at the Row like a month ago. This is the kind of decoded image from one camera's perspective. So after we take those 40 pictures, we decode it, and every pixel has a kind of color code. So if it's more red, then the farther it is to the right in the projector space. If it's more green, farther it is to the bottom of the projector space. So like a really yellow pixel would be bottom right, really black pixel would be top left. So each one of these, this is like one reflection, another reflection, another reflection. Sometimes they overlap and we can't really untangle them. And sometimes they're really sparse, like there's one, there's another one, there's another one. Other times they're really dense. Yeah, we can take that and then this is where it gets really weird. So the camera was pointed at the ceiling, right? It's a little hard to tell, but there's a column in the middle of the space, and the disco balls are actually like below where the camera's pointing right now. We're looking at the ceiling where all the light's bouncing off the disco balls and hitting the roof, hitting the ceiling. If we take that image and we kind of invert it, so we take every pixel in the projector space and we say, where did this end up in the camera space? You know, top left pixel from projector space, where are you? And we check and we say, oh, here, I found it, the black pixel. It's at this position. And you keep going and you're like, maybe this kind of slightly yellowish pixel towards the bottom right of the projector space, where is this? And you look through and say, oh, I found it. This is where that came from. Then you get this image. Now this is amazing because actually we just took a photo from the projector's perspective without looking at the same thing that the projector was looking at. We were looking at the ceiling and somehow we got this image from a completely different perspective. It's like we're looking around a corner. We basically inverted the role of the projector. It's not really a projector anymore, it's more like a camera. So same as before, red means came more from the right side of the photo, and green means more came from the bottom of the photo. We're not done yet, because we don't know where these pixels landed in 3D space. We only know where they are in the 2D camera image space. So we have to build a 3D model of this space. And this part's pretty manual. I just go around with a little rangefinder, like it's kind of like a tape measure, but I can just point it at something and know how far away it is. And I just make a lot of notes in my sketchbook, and then I use a software called SketchUp to make a model of the space. Once we do that, then we have to figure out where was that camera that we took that photo from. And I built another tool for this that basically lets us click on a few points that match between the photo and 3D model. And that software figures out where the camera must have been for those points to end up in that place in the photo. So you kind of drag the points around and it sort of figures out. It looks like the model's changing, but really what's happening is the camera's changing. So the field of view is changing, perspective, position is changing. Okay, we're almost there. So if we render the 3D model from that predicted perspective, then we get this other kind of coded image. And this is like a 3D version of those 2D things we were looking at before. Remember before, red was more to the right, green was more to the bottom. Now we've added blue, which is like the depth. So if we've got a color that's white, it's going to be in like the far top corner of the space. If we've got a color that's black, it's going to be like the near bottom corner of the space. And then there's everything in between. All right, and this is the last step, really. So we take everything we've done up to this point and we combine it into one last image down here. So instead of just knowing where the pixels came from in the camera space, we've got the pixel locations in 3D. And we combine this across the multiple scans because we can't get all of the reflections at once with one picture because no camera has a wide enough lens. So we take a few of them and we combine them. And we get this kind of mega scan that covers all the reflections in the room. So again, what this tells us is when we project from projector number 1 at this position, the reason it's kind of red is because it's at the bottom far right corner of the space. So the X value is high, the red is high, but the green and the blue are not really there, so those values are close to 0. All right, that was it. Now that we know where all the pixels end up, we can just write some code to evaluate a volumetric function across the space. We can't just project like 2D images or video, so we have to describe everything that we want to render in the space as this kind of 3D function. That means that when you see like some concentric circles or some stripes, what you're actually seeing is a kind of slice of a 3D shape. So these are concentric spheres, and those are slabs of light. And we're looking at the intersection. Every reflection acts kind of like a little portal into this volumetric function filling the space. And the first time we installed this piece, we were really captivated by all these emergent details that we hadn't thought through. Like, depending on where you focus the projector, it's possible for a single pixel to actually end up in multiple locations around the room. That's kind of mind-blowing. How do we deal with that? Or, each of these reflections will show a subset of the same image. Or that when you stand in front of the projector after the whole calibration is complete, you actually get an image of the disco balls projected onto you, because what the projectors are projecting is an image of how the room would look if that volumetric function was filling the room. But I think most of these people who see light leaks don't have any clue about any of this whole process. They step into there, they kind of are like overwhelmed by the amount of reflections and the light and how shiny the disco balls are. So most people just kind of upload like pictures like this of the disco balls in all their glory. And I'm happy with that, because for me, my favorite art's accessible in a lot of completely different ways. A few dozen disco balls in a pile will always be completely entrancing, and there's no way to get around that. One of my favorite sides of the piece is actually when we're hanging the disco balls in a net. Sometimes we get to go up to kind of like on a, like on a ladder or something to kind of place them into the net, and we get to see the disco balls from this kind of dark side, like the side that they're not projected from. And I can't really explain it, but it feels kind of like each one's a prism for gazing into some otherworldly starry sky. It feels like you can't really see the disco balls anymore because of the way they're reflecting things. So I totally get like what people are feeling when they post the photos of the disco balls. But for me, like the best version of light leaks is this kind of fleeting imaginary sculpture that a visitor will construct in their head if they can kind of suspend their awe long enough to ask, how does this work exactly? And my favorite question I've ever gotten about light leaks was someone who like sat in the corner for 15 minutes. And I thought they were just kind of soaking it up like everybody else, but they came up to me afterwards and said, I have to know, where was the light coming from? And I think they really understood what was going on there. So when we first installed light leaks on that last day, before we took it down, we brought in a haze machine just to see what would happen. And I felt like I could finally see this imaginary sculpture directly, reified, suspended in the air. It's like when the detective pulls out some special tools and uncovers all the fingerprints, suddenly the crime comes into focus. But this experience of walking through this forest of beams is almost too compelling, almost too easy. So for me, I really appreciate, and I kind of want to keep it like just in my head, this really powerful experience of the geometry that kind of can only ever exist in your mind, and the process of walking through to get to that point. So thank you very much, and thanks for having me.